Hello everybody, this is Matt with mattsmath.com. Thanks for joining us as we talk about independent and dependent events today. We're in the Common Core Standard of Probability and Statistics, and we are most likely going to be trying to guess what's going to happen using probability today. Not going to be looking at much samples, but definitely looking to see what would be most likely happening. All right, a guiding question is, what is the difference between independent and dependent events, and why on earth would you need them? All right, well, when we have independent and dependent events, we have green and purple tennis balls. Seriously, there they are. All right, so what we're going to do today is we're going to draw some of these as if we were putting them in a bag and pulling out a green tennis ball or a purple tennis ball, okay? So let's do that. Let's try our first one. First experiment we're going to do is we're going to grab two green tennis balls. That's what we want to happen, okay? Now, let's see what actually could happen. Well, if we put all of these in a bag, we have three tennis balls, two green, one purple. And notice I'm going to talk about my first draw. I'm drawing them at the same time, and essentially when we draw them at the same time, we do a first draw and then a second draw. Well, what are my options? My first option is one green ball, another green ball, or a purple ball. Okay? Now for the second draw, I've already taken one ball out, and now I'm going to draw another one. Well, what's left? After I've taken one green ball out, what's left? Well, there's one green and a green. That's what I could draw. I could draw a green and a green, and I could do a green and a purple. Those are my two options for those guys. What's my option for this one? Well, if you said there's no difference, that's true, because the same thing's going to happen here. If I draw a green one, what's left? There's a green and a purple, so I could draw either one of those. And then if there's a purple, there's only two green left, so my possibility is purple-green, or this one is purple-green. Okay, so this is the chart that we're going to draw. Is first draw, I could get a green, or a purple. And then on the second draw, if I take the first green out, I could get the second green. Or I could get the green and the purple. Or I could draw the second green and the first green. Or the second green and a purple. Or if I draw the purple, I could get the first green and then the purple and the second green. Make sense? So how many different ways are there to grab two green tennis balls? Well, here's one. Here's another. Out of how many different opportunities? 1, 2, 3, 4, 5, 6. So 2 possibilities out of 6 total. That would be our probability. Let's do it a different way. Now we're going to take a green tennis ball, put it back, and then grab another green one. Does this change our probability? Let's see. See how this experiment happens. Again, first opportunity I could get is drawing the first green, or I could draw the second green, or I could draw purple. All right, and then we're going to put that ball back in the bag, and we are now going to draw it again. Well, if I put this ball back in the bag, there are still 3 tennis balls in there. There's a green, and a purple. So my 3 options are, if I put this one back in, I could draw that same one again, or I could draw the other green one, or I could draw the purple. And then if I draw the second one the first time, I have the option of drawing the first one, or I could draw the second one again because I put it back in the bag, or I could draw the purple one. And then if I draw the purple the first time, I put it back in the bag and I could draw the first one, or I put the purple back in the bag and I draw the second green, or then the purple. So here's now our different options. Notice there are more options available because we put the ball back in the bag. We wanted 2 green tennis balls, so how many different options are there? There's 1, 2, 3, 4, out of a total 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4 out of 9 is the probability here. All right, hanging with me there? All right, let's talk about what actually happens then. What's the difference between the 2 experiments? You notice any differences? Well, I hope you would have said that the first one, you actually take the ball out and you leave it out. And then on the second one, you take the ball and then you put it back in the bag when you're ready to draw it. That is the major difference between the experiments. And notice there are less outcomes here than there are down here. There are less outcomes here than there are here. There were a total of 6 here. There were 9 here. And as we just said, it does affect the probability. How much? Which experiment would you rather do if you were betting some money on getting 2 green balls? All right. Well, how do events affect each other? That's really what we're looking at today. And depending on what you do, whether you put the balls back in the bag or you keep them out of the bag. It really affects what's going on. Well, if I flip a coin, looking at that, the next time I flip it, usually it doesn't depend on the next flip, right? Whereas if I draw letters from a bag, I pull a letter out of the bag and I keep it out of the bag, that affects the event the next time around, doesn't it? Whereas with a coin, not really affecting the next time I flip it. Nothing happens to the coin when I flip it. So these are the two different types of events that we're going to look at. First one is called independent. And as you might guess, independent does not depend upon the other events. So the first example we looked back wasn't independent. It did depend because I pulled the ball out and I left it out. The second example, where I put the ball back in the bag, would have been independent because the second event did not depend upon the previous one. And here's how we find it. The probability of getting A first and then B, well, here's what we do. We take the probability of A, the first event, and then we multiply it by the probability of the second event. What's the probability of the first thing happening, and then what's the probability of the second thing happening? And nothing changes between the two events, right? Because they're the same event. So let's look at it this way. Flipping a coin 4 times, no matter what comes up, and getting 4 heads. I want to flip a coin 4 times, and I want to get 4 heads. This is independent, right? The previous flip of the coin doesn't affect the next flip. So let's flip a coin 4 times, and let's talk about the probability and what happens. All right, here's my event that I want. I want a probability of getting a heads, and then a heads, heads, heads. Well, the way we find this is take the probability of getting 1 head when I flip it. And then I multiply it by the probability of getting 1 head, and the probability of getting 1 head, and 1 head. Well, what's the probability of flipping a head? It's just a half. It's 0.5. So 0.5, and then what's the probability here? Same thing. Probability here, same thing, same thing. So it's just a half times a half times a half times a half. That's the probability of getting 4 heads in a row. Multiply them together, we get 0.065 or a 16th or 6 1/4. All right, now dependent events. Now this is the first experiment that we did where we took the ball out of the bag and we kept it out of the bag. It's an event that does depend upon other events, okay? And the way we find it here is we take the probability of A, then B, and that equals the probability of A first. So imagine taking that 1 green ball. What was the probability of getting the 1 green ball out of 3, 1 out of 3? Well, if we take the 1 green ball out, now there's only a 1 out of 2 probability because there's only 1 green ball left. Let's look at a real example here. Here are some letters. We have the letters C, C, B, 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 and A in a bag. And I want to pull the letters out in this order, C, A, B. I'm going to pull them out. I want to pull C first. I'm going to pull A out and then a B. And then when I draw it, I want to keep it. I'm not replacing it. Notice here, not replacing. Usually in any experiment that says not replacing means it's dependent. It depends on the previous one. All right, ready? Let's draw it. Well, what's the probability of getting a CAB is what we're looking at. Well, first we have to take the probability of getting a C, keeping that letter. What's the probability of getting an A then, keeping that letter, and then what's the probability of getting a B? All right, well, I start off with 6 letters, right? How many C's were there, do you remember? There were 2. So the probability of getting a C is 2 out of 6, or 1/3. Now I keep that letter, so how many letters are left in the bag? There's 5. Okay, I took 1 C out. I didn't take 2 C's. I took 1 C out, and I now have 5 letters in the bag. I want to draw an A, and how many A's were there? There was only 1. So I take 2/6 times 1/5. Now I've taken the A out of the bag. Now how many are left? I took 1 A out, and now there's 4 left. How many B's were there in the bag? There were 3 B's in the bag. So I take 2/6 times 1/5 times 3/4, and that will give me the probability of getting CAB in that order. Here it is, 0.05 or 1/20th or 5%. I have a 5% chance of drawing a C, then an A, then a B. All right. Let's test your knowledge real quick. Are these events independent or dependent? You spin a game spinner twice. The first spin is blue and the second spin is yellow. Is that independent or dependent? Next example, you're rolling a number cube. You roll a 6, and your second roll, you roll an odd number. Is that independent or dependent? Well, you and a friend are playing a game, and you both randomly draw a playing piece, and you get to go first. Well, you first draw a red piece and keep it, and then your friend draws a blue piece. Is that independent or dependent? What'd you get? All right, with a game spinner, these spins are not dependent upon each other. Right? No, it doesn't affect it if I get a blue first and then a yellow. The game spinner, it's not affected, so therefore it's independent. Same thing with number 2. When you roll a die, the roll of a 6 and then you get an odd number is independent of each other. It doesn't change the probability. Whereas in number 3, I drew a red piece first, I kept it, that's what I was going to use, and then my friend drew a blue piece. There weren't the same amount of pieces in the bag or wherever you're drawing them from because I kept the red piece. Okay? All right. And if you remember at the beginning of the lesson, we talked about tree diagrams. I didn't mention that, but that's what they're called. They're called a tree diagram. And we're going to use these because they could potentially be helpful for you. What's the probability of flipping a coin and getting 2 heads? Well, let's do this by doing a tree diagram. Again, we have the first flip and then the second flip. On the first flip, I could get what? I could get a tails or a heads. So I start with the tree diagram here. These are my 2 options, first of all. Okay, now I want to get further into it and do a second flip. What's possible my second flip? Well, if I flip it and get a tails, I flip it again, I could get either a tails or a heads, right? And in here, I could also get a tails or heads. So these are my options. So I could get a tails for the first one, or I could get a tails and a heads for the second one. Third option, I could get a heads and a tails. Fourth option, heads and a heads. And that's the one that I want. I want to get 2 heads. And then here, these are the outcomes. So there's 1, 2, 3, 4 possible outcomes. How many of them are heads, heads? Well, there's only one of them. One option out of 4 is heads, heads. So the probability would be getting 1 out of 4. So this is actually a visual way for us to represent the probability, where instead of taking how many heads here, there's 1 out of 2 possibilities, and then there's a 1 out of 2 possibility here, multiplying 1/2 times 1/2 gives us 1 out of 4. Same thing. All right, why don't you do this one on your own? What's the probability of flipping a coin and getting tails and a heads in any order? Doesn't matter if you get tails first or heads first. All right, what'd you get? Well, remember, there's 4 possible outcomes, tails, 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 heads, heads, tails, and heads, heads. I have 2 possible outcomes here. I want tails, heads, or heads, tails. So 2 out of the 4, it's 1/2. Doesn't matter what order it was in. It's 1 out of 2. All right. Work with these guys. Here's a tree diagram of rolling 2 dice. The top row is the first roll. So here's the first roll, and the bottom row is the second roll. I could get a 1, and then I roll it again. I could get a 1, 2, 3, 4, 5, or 6. My first roll could be a 2, and then I could get a 1, 2, 3, 4, 5, or 6, or so forth. What's the probability of rolling a 5 and then a 3? And you roll an even number on each roll. What's the probability of that? All right, remember, you're going to want to be able to count the amount of outcomes that actually happen. There's 6 here, 6 here, 6 here, 6 here, 6 here. So there's a total of 36 outcomes. How many outcomes are there of rolling a 5 first and then the 3? Well, let's go to the 5 and then the 3. Are there any other options where there's a 5 and then a 3? There's not. There's only one option. So it's one outcome out of the total 36. And rolling an even number is a little bit different. How many options are there down here for rolling an even number both times? Well, I didn't do an even number here, so scrap those. Even number here, so there's 1, 2, 3. Even number? Nope. Even number? Yep. So I was at 3, 4, 5, 6. Even number? Nope. So scrap all those. Even number? Yep. So I was at 6, 7, 8, 9. 9 out of the how many outcomes? 36. 9 out of the 36 reduces down to 1/4. All right, during a card trick, your friend asks you to take 2 cards. First card you draw has to be a heart, and the second has to be a diamond, and you don't put it back in. So what's the probability at the beginning of getting a heart? Well, there's 13 out of 52, because there's 13 hearts, 1 out of 4. Now, you took that 1 heart, and now you keep it. So how many cards are left? Ah, that's the trick. There's 51 cards left, okay? Now, what's the probability then of getting a diamond? Well, now there's 13 out of 51. So then you multiply those two probabilities together, and bam, you get this, 13 over 204. All right, well, that's pretty much it today. Are you able to tell the difference between independent and dependent events and why you would need them? Biggest reason is the independent events don't matter upon the previous event, whereas dependent does. All right, well, thanks for joining me as we talked about independent and dependent events today, probability. This is Matt with mathsmath.com. Thanks for joining us. Check us out on Facebook at Solving Maths Problems, on Twitter, Maths Math, and enjoy math.